Good morning, everyone. So we can start this morning session. So it's a great pleasure to have Professor Kerr with us here. I believe everyone in this audience know Professor Kerr, so he doesn't need any introduction. Just to say that his construction of the Kerr geometry had a fundamental contribution in GR. So we heard a lot of the Kerr black hole even yesterday, and we will hear more today. So it's a great pleasure to have Professor Kerr here. So Professor Kerr, go ahead, the stage is yours.
Okay, well, it's been a great pleasure to be in Iran, at least by proxy. The talk I'm going to give today is going to, I'm going to try and show how ideology has taken over a lot of areas in the relativity. Now, I'm going to start with my idea of what the Kerr black hole represents. As everybody knows, there's an inner horizon, an outer horizon. In between, you've got what I like to call the event shell. The actual horizons themselves aren't all that significant. I mean, if you got even close to one of the horizons, you're in serious trouble and are going to end up falling through. I mean, you have to, the velocity you need to avoid falling through is tremendous. Okay. Now, what's my picture of a black hole? We've got this solution here, which is about the only one for known solution for a black hole. But how close is this to reality? Well, first of all, in order to have any solution, you've got to have a source. It would be, if I could present a black hole which didn't have a singularity inside or a neutron star or some object to generate the field, then relativity would be in trouble because you would be generating fields from nothing. So the fact that this has got a singular ring inside is no more significant than the fact that Newton's theory of gravity says that the force is m over r squared, which we all know isn't true at the center of the Earth. In the center of the Earth, the field drops off. Now, in order to see what I believe about this black hole solution, I'd like to just give what happened there? Sorry, I'll full screen again. Yeah, something happened. Then let's take a neutron star. Okay, let's suppose that in the process of becoming a neutron star, we have the explosion, out goes all the matter into space, then it starts returning and forming an object, the neutron star at the center. Now, as the neutrons come back in, the star is going to get larger and larger. Now, we know what happens as it approaches 3 solar masses. It's going to shrink. You know, you can, 2 solar mass might be 10 times the diameter of the sun's black hole. But as that neutron star increases from more matter coming in, it's actually going to start shrinking. Now, if it weren't spinning, I have no idea what will happen. You know, we've got the Schwarzschild solution, but which seems to have a singularity in the center. This depends upon how matter behaves under intense pressure when it becomes really compressed. We don't really know whether the matter continues to satisfy a gas-like equation of state or whether it changes if it were classical, and it's not even classical. So now, the dominant thing here is the spin. And from the Kerr solution, you can see that inside this event shell, there's an area where you can travel outwards towards the inner shell or inwards. The one place you don't want to go is anywhere near that pseudo-singularity in the center. Now, how can this be? First of all, there's no trapped surface in that central region. There are trapped surfaces in between the two horizons. I'll talk about these later, but inside there's no trapped surface. So that's a little bit of a problem for people who talk about the inevitability of singularities. Now, why is that? That's because of the angular momentum or the centrifugal force. I like to split the force up into Newtonian type attraction, the centrifugal force, which is dominant at the inside the inner horizon, and also the exchange forces between the particles, which tend to keep it apart. But I don't think those are all that significant at the end. I think inside here, what the two forces that are going to dominate are the centrifugal force due to the angular momentum and the attractive Newtonian type gravitational force. Okay. What I see is that at some value of the parameter R, the collapsing neutron star will reach some sort of equilibrium where it will not collapse anymore. And all you'll have is a neutron star, very dense, denser than a typical one that is not a black hole, but and spinning extremely quickly. I think neutron stars are limited to about, what, 20 revolutions a second, or a revolution every 20 seconds or something like that. Inside, it's going to be spinning a lot quicker. Okay, so that's what I see. I see no singularity, nothing very unusual. All you've got is a neutron star spinning like crazy with the a region where the attractive forces are so strong that you can't escape through that event disk, the shell between the two horizons. Now, here are some representations of Kerr. There's the Boya Lindquist, which was actually shown to exist by Achilles Papapetru beforehand. He showed that whenever you've got a stationary axially symmetric solution, if there's no singularity along the axis of rotation, then it can be put in its simple form with only one cross term, a d phi dt term. Okay, now to go from Boya Lindquist back to Kerr-Schild, which is actually the original form I gave the metric in before Alfred and I found all the Kerr-Schild metrics, then it's a very simple transformation. You just change the t and phi coordinates. This metric does not depend upon t and phi. So this is, you add a function of r onto each of them. And the function of r depends upon r. Okay. Now this gives you the ingoing and outgoing Kerr-Schild. The the original form that I gave the metric in was ingoing Kerr, which is, with either the plus sign or the minus sign here. I don't really care which it is. It's one of them. You notice that these transformations, either to ingoing or outgoing, are almost identical except for the signs. One of them, one time you have a minus, the other time a plus. And the reason for this is this metric is independent of the transformation in t goes to minus t and phi goes to minus phi. And that's, well, it's partly because it's a solution with two principal null vectors at every point. Now, if we took this was the original form I gave Kerr in, we can transform it to a Cartesian form in which it's just Minkowski space plus the square of a null vector. Okay. Now, why do people think it's got a singularity? Well, it all comes back to Ray-Chuduri's equation. Back in probably about the same time I found my solution, or soon after, in other words, in the early 60s, Ray-Chuduri proved a theorem that if you have a set of null rays that were satisfied certain conditions, then they would have a singularity at the end. They cross. Is this theorem true? Well, it's pretty debatable, but there was in his theorem about which is used to prove singularities, there's a caveat that you have to assume that every light-like ray has infinite affine length. Now, people think of this affine length as being something like the length of a time like geodesic, but it's nothing like that. You see, there is no real measure of distance along a light-like curve. The distance is zero along it. So it's really wishful thinking to think that this affine parameter, which is just basically a vector which is transported by an affine transportation along the null ray, it's wishful thinking to believe this is like an ordinary geodesic. Now, I'm not going to, here in the next slide or two, I'm going to explain that in the Kerr solution, there are lots of null rays of finite affine length. Now, this completely destroys any attempt to prove that there's a singularity inside, because the best known singularity theorem by Roger Penrose, what he proves is either there's an affine, either there's a light-like ray of finite affine length, or there's a singularity. Now, what I'm going to show is there's lots of light rays of finite affine length. In between the two horizons, at every point, you've got a principal null vector. This is a double root of the, it's a repeated root of the curvature tensor. Kerr happens to be of type D, and it's got two principal null vectors at every point. Now, on the horizons, the generator of the horizons happens to be one of these principal null vectors. I mean, what else could it be? It's bound to be some invariant vector, and it happens to be one of these. It's what you might think of as the outgoing principal null vector. except it's not outgoing at this point. It's traveling along the horizon. So at each point on the horizon, there's a principal null vector which is staying on the horizon. The effect of this is that if we take this second set of principal null vectors, not the incoming one, which was used to generate the Kerr solution, if you like, but the other one, then it's trapped in between the two event horizons. Okay, now, it can't cross if you start at any point between the horizons and travel along that principal null vector, it can't cross one of the event horizons, because that would mean that at that point there are actually three principal null vectors, three repeated ones, and that's too many. You can't have that. So from a geometrical point of view, it's clear that these principal null vectors are trapped. Now, it's also true that the radial coordinate r is an affine parameter along each of the principal null vectors. That means, if this is true, and it is, if that's true, then the affine parameter, what happens to a principal null vector is that it starts asymptotically at t equals minus infinity, the outer, down. I'm trying to go up. Yeah, it starts at the outer horizon, asymptotically there, and it falls through to the inner horizon, and it's asymptotic to that. So the I've actually calculated it here, but the total, the difference in R between the inner and outer horizons is just the difference between R plus and R minus the values of R at each of the horizons, and that's finite. So what I've shown here is that at every point in between the horizons, there's a light-like ray of finite affine length, which never leaves that event shell. Now, there is clearly no singularity in between the horizons, so there's no question of being one there. What happens inside the inner horizon? Well, given that there's actual body there and not this stupid singular ring, which is forced on me because there's no matter in my solution, given there's a body there, what will happen to the light rays that actually penetrate into the inner region is they will tend to go through it and be asymptotic through the body and be asymptotic to the inner horizon at the other side. So the principal null vectors will end up approaching the inner horizon from each side. So actually there's lots more geodesics of finite affine length. Now, but what about a trapped surface in between the two? Well, here I quote my Persian cat's famous theorem, there's hairy ball theorem. Her name is hairy ball theorem, my cat. And it's usually stated that you can't comb the hair down on a ball without having one bit sticking straight up. Now, another slight generalization of that is if you have a ball-like surface and you have two sets of vectors pointing out of it, one is the normals that Roger Penrose talks about, The other is the principal null vectors that I'm talking about. You have both of these fields defined on a trapped surface. And it's a simple matter to show that in at least two places, not just one, at least two, these vectors coincide in direction. So at least two of Roger's normal vectors that he says surround the particle in the inside and cause singularities, at least two of these vectors are actually principal null vectors which never leave the inner, they never leave the event shell, and they have finite affine length, and they're not singular. Now, some desperate people have countered this by saying, what about the maximal analytical extension of Kerr? Well, all I can say to that is that any extension of Kerr is occurring after the end of time. I mean, it's not occurring in Googleplex years, it's occurring at an infinite time in the future. In other words, it's not occurring. I could say more about it, but that's even if you look at this so-called maximal analytical extension, even if you look at that, there is no proof that any extension of the vectors I'm talking about end up at singularities, because all you've got in this pseudo future is a similar set of copies of your neutron star inside a black hole without a singularity. So this is a typical example, that, as I see it, of how people believed 60 years ago that singularities had to exist in black holes. And it didn't matter how many times the proofs were found to be faulty, it wouldn't matter, because they were believed. It was believed it had to be true, and therefore we'll just find a better proof. Now, this is exactly what's happened with Stephen Hawking's evaporation of black holes. Every time somebody notices there's a problem with the proofs, out will come something else which they hope will fix the problem. The real problem is that after 60 years, there still isn't a proof that black holes evaporate. The biggest problem is there still isn't a really good theory of how quantum mechanics and general relativity coincide. And I remember seeing Stephen's first theorem. Here, we've lost that again. It's my cat. The hairy ball has done it again. About the middle of the 60s, there were a number of singularity theorems floating around. Now, the first two that came to Austin, Texas, where I was, were presented, I think, by graduate students, really, from elsewhere. And in each case, I managed to construct a counterexample during the course of the lecture, and so I never heard of them again. Then Stephen came to Austin with his a theorem that said that either you were going to get black holes in the future, singularities in the future, or you would get closed time-like loops. Now, he didn't give us a talk because he was, I think, visiting George Ellis for the weekend. He was only there for 2 or 3 days. So he said he used Race-Duri's theorem. So for the next 2 days, I thought about this myself to try and see if I could prove what he said. And at the end of the weekend, I said to George Ellis and Stephen that I couldn't prove exactly what he said about a closed time-like loop occurring. All I could prove was that you could get almost closed time-like loops. Well, 2 or 3 months later, his theorem came out, and it had been replaced by what he said he could prove with what I said I could prove, which was that there were almost closed time-like loops, and there was no acknowledgement of anything I said, of course, but I believe in Hawking and Ellis that some credit was given to me for this. The thing about it all, of course, is it all goes back to Race-Duri's theorem. So it's not really true, the theorem. All the theorem shows is that there are light-like rays of finite affine length. Okay, now.
Sorry for the interruption. Sorry for the interruption. We have 5 minutes left. Please.
Yes, I just noticed that. This has taken far longer than I meant to. Okay, now what I really wanted to talk about was equations of motion, the two-body problem. There are some slides here in which I describe the original Einstein-Infeld-Hoffmann papers. For the 20 years from 38 to 58, Infeld and Einstein, to some extent, kept trying to prove that you could have a consistent theory of equations of motion for bodies, interacting bodies. And their original paper used an integral. You'll have to read this for yourself. I actually showed in my work for my PhD thesis that there were, of course, there was not only the equations of mass and motion, there were the equations of angular momentum. So there were extra ones. I also showed at that time, which was not the way people looked at it, that at the same time as you expand the metric, you also have to expand the equations of motion and angular momentum, everything. And that then, if you did this, that you could solve the equations. Now, I did this for the fast approximation and the slow. Actually, at the time, I calculated the non-trivial equations between arbitrary multipoles and arbitrary spinning particles. But that I did not publish that lot for reasons which I won't go into. Now, the Kerr-Schilde approximation is what I did want to mention. I'll only take 2 minutes. You can read this for yourselves. When I was in Texas 3 or 4 years ago, Ramo Ruffini said that he suggested that Jose Rodriguez look at whether he could generate the equations of motion for two black holes coalescing simply by using the approximation where each body moves in the field of the other, the test body approximation. And a week or so later, he told me this is what Jose was going to do. Jose and Jorge Rueda as well was Jose's advisor. So it seemed like about a week later, they came in and said that, yes, it had all worked out. And furthermore, they were getting just the same results as LIGO. a almost complete agreement. But this was from a first approximation. Now, at the time I yelled out, it's the Kerr-Schild approximation. You see, if you're going to look at black holes, instead of starting with some stupid radiation gauge or something like this, there's no reason not to start with the Kerr-Schild approximation, because in the Kerr-Schild form, the linear approximation to the field is actually exact. The exact field is flat space plus a term proportional to the mass. So you can take two of these bodies and do something which I talked about 60 years ago, was to do something either similar to the fast approximation or to the Einstein-Infeld-Hoffmann, to calculate the forces between. Now, there's not a lot of point in doing that, because if Jose and Jorge and Remo are correct, what they did using, which used, by the way, the Boya Lindquist form, which is not really a very appropriate form for this problem. They used that, and but it gave excellent results. The reason being that the two-body problem, LIGO, is looking at the far field. And when I say far, I mean a hell of a far. So what happens in close to the actual collision of the particles is pretty irrelevant. And if you talk about the in-out time, the time for a signal to go in and come out, that's too short. So it's too long. Anyway, you can read this, and I have to finish now. Obviously, I spent far too much time on this first bit. So that's my talk. Thank you.
Great. Thank you, Professor Kerr, for the nice talk. So you're right on time. So we have time for perhaps one question.
Yeah, can I ask a question?
Sure, go ahead, please.
Yeah, my name is Maurice. Roy, you spent a considerable amount of time in your very clear account of the Kerr metric on the formation of singularities. Of course, if you look at your actual Kerr solution, the stationary solution, wouldn't it be sufficient to say that that solution as a limit naturally contains singularities already by Liouville's theorem? In particular, if you look at the Kerr-Schild solution, that makes it very explicit that asymptotically you're looking at a Minkowski spacetime.
No, of course it's got a singularity. That's an empty solution. It's got no matter in it. It's got to have something. Now, if you take a real physical situation, then you're going to have to take, say, some R value less than the inner horizon and fit a source, a matter source inside. Now, this is a lousy way to go about it. It's always bad to have to take a complicated exterior solution and fit an interior. I mean, what one really should do is take an interior, which is a neutron star that's too dense for, shall we say, take a neutron star which is 10 solar masses and spinning it with an A value that's a half. Now, the ratio of the angular momentum to the mass. There's no singularity involved. The singularity is a red herring from the fact that my solution happens to be empty. It had to have a singularity. You could say the same, as I said before, about the Newton's gravitational field around a spherical body. It's not
Yes.
singular at the center, but Newton's m over r squared looks singular. Of course, the field inside the body changes. And the field inside a body, inside my inner horizon, changes. It's not that Kerr solution with a singularity.
May I have a comment?
Go ahead, please.
May I? Dr. Firouzjahi, may I have a comment?
Yeah, go ahead, please.
This gentleman who raised the question of Liouville's equation, and first of all, I'm requesting him to talk to me later after the meeting. But in respect to his comment here, Liouville's equation invites in a distribution. And when you make an interaction between a distribution and whatever dynamics that there is a singularity in it, this interaction removes the singularity. Let me repeat again. You have one dynamic system with a singularity, and then you are talking about distributions of it through Liouville's equation or through quantum mechanics, which there is a distribution, extended wave-like thing. This interaction removes the singularities and in a very fundamental way. It is only sufficient. It's only sufficient to include such a term in the Lagrangian or whatever action principle that one is talking about.
So, thank you very much. I guess we are behind the time, so I suggest we keep the discussion after the session if possible. So for the interest of time, I thank Professor for the comment, and let's go for the second speaker.
Just one comment. Just one comment. This topic is very hot, and of course, a difference also is that the syntonic flat in around the neutron star is not empty, but as a magnetic field to the Papa-Petro equation, and this will be discussed by Jorge. Well, very exciting and very beautiful talks, and as usual, let's thank Kerr for the beautiful presentation and the very thoughtful ideas. Thank you.
Great. Thanks, Professor Ruffini, for the comment. So we go for the second speaker of the session. It's a great pleasure to have Professor Shing-Tung Yao with us. Professor Yao is a renowned mathematician. He made fundamental contributions in the fields of differential geometry, partial differential equation, mathematical physics. He is the recipient of many awards, including the 1982 Fields Medals in Mathematics for proving the Calabi-Yau conjecture. So the Calabi conjecture, which is now Calabi-Yau, part of the string theory, I mean, the fundamental application in string theory. So it's a great pleasure to have Professor Yao with us. So Professor Yao, the stage is yours. Go ahead, please.
Okay, thank you very much indeed. It's an honor for me to give this talk. Can you hear me? Hello?
Yeah, I hear you well.
Good. Okay, today I'm going to talk about a simple but important topic, angular momentum to a distant observer from now infinity. So, of course, we know the famous experiment that was done a few years ago, and that gravitational wave from a binary black hole merger, and we see a gravitational wave that was the triumph of the general relativity. But here I want to understand the following question: measuring the angular momentum carried away by the gravitational wave. And what is the angular momentum of the system before and after? The problem comes out of the following fact. There's a super translation ambiguity. This is a problem since the 1960s. And the angular momentum recorded by two distant observers of the same system better be the same, but the way that the quantity was proposed by many authors are not the same. So I'm going to report on the work that I did recently with Punnan Chen, Jordan Kerr, Muda Wang, and Kika Wen. So these are younger gentlemen who has done the fundamental work, which I truly appreciate. The papers appear here, 1, 2, and 3, and I think you can find it in archive. Some of them are already appearing in the journals. So the outline of the talk would be the angular momentum in classical mechanics and special relativity, distant observer in the Bondi-Sachs formulation in general relativity, super translation ambiguity, and also the definition we proposed, namely by Chen, Wang, and myself about 5 years ago. So this in classical mechanics, of course, we all know the angular momentum particle is defined as J mr cross r pi. So, and the ambiguity due to the coordinate system is shaped by the linear momentum, which should be the same when we do our calculation in general relativity. Well, the special relativity can be formally in terms of geometry of the Minkowski spacetime. The continuous symmetry of the Minkowski spacetime consists of these vector fields. They generate time translation, spatial translation, rotation, and Lorentzian transformation, respectively. And Noether's theorem states that each continuous symmetry corresponds to a conserved quantity. So for a particle in Minkowski spacetime, we got energy, we got linear momentum, we got angular momentum, we can send a mass by using the velocity vector of the particle, dot product with the translations, the symmetries. So this is all well known to you. If we translate the coordinate system, t to t plus alpha naught, xi to xi plus alpha I, then the linear momentum and the angular momentum will shift according to this formula in the bottom. It's all well known. Now, let's come to general relativity, where we have Bondi-Sachs formulation. So we have an idealist distant observer situated in future now infinity, I plus, where light rays approach along now geodesic, as you see from the picture. The description of I plus of an isolated gravitational system was by Bondi and Sachs in 1962, several papers. And then Penrose also has a conformal compatification in 1965. And the more rigorous description was due to Christodoulou and Kahneman in 1993. So Bondi, Sachs, and Penrose formulation are essentially equivalent. Both of them imply the spacetime have some kind of peeling property. These are idealized properties that may not hold in general, as was demonstrated in the work of Christodoulou and Kahneman when they discussed about perturbation of Minkowski spacetime. This, of course, also appeared in the thesis by Lydia Beria, who was a student of Christodoulou. We can describe the now infinity and distant observer using the Bondi-Sachs formalism. The result can also be extended to polyhomogeneity, as was discussed by Roussel et al. So recall the Schwarzschild spacetime in Eglinton-Finkelstein coordinate can be written in this form. I'm now describing the Bondi-Sachs formulation. So M is the mass of the black hole, and we get sigma AB to describe the sphere, standard sphere. And U is a retard time, and R is a luminosity distance from the black hole. So this, of course, is familiar to all of you. And I plus corresponds to R equal to infinity. In this panel's compatification, you can see it. U equal plus infinity corresponding to future timeline infinity, I plus, and U equal minus infinity corresponding to space-like infinity, I plus, I zero. Now, Bondi and his collaborator postulate a coordinate system, which we call Bondi-Sachs coordinate, in which the metric tensor of the space-time is given in the following form. So minus UV du squared minus 2u du dr plus r squared HAB dxa plus WA du dxb plus WB du. So we shall, as Bondi and Sachs assume, the space-time is assumed to be asymptotic flat in the sense that U and V will go to 1, HAB go to the standard metric, WA go to 0 as R go to infinity. And we fix a condition determinant, HAB is equal to determinant, sigma AB, the standard metric for R large. Now, the important assumption that Bondi and Sachs make is that this for outgoing radiation condition is imposed so that all the metric coefficients can be expanded in the power series of 1 over R. This is really an assumption. An assumption is relaxed to polyhomogeneity by Purcell and his friends. And this assumption was somewhat relaxed, but it still cannot be proved to be true without any condition. So, well, Bondi and his co-authors and his followers found the physics of gravitational field can be encoded in the coefficient of the power series expansion of all those coefficients. The first thing is the energy and linear momentum. The expansion, capital V, that we wrote down earlier, is expand, and it is 1 minus 2 mu x over r plus big over r minus 2. M is called the mass expand, and this corresponds to the total mass of the black hole. The Bondi-Sachs energy momentum is a 4-vector associated with a U equal constant slice. Is defined by integral of 2 mu. X is sitting S2, we integrate it. PKU is the linear momentum, which we also integrate M against the coordinate xk. So this gives rise to the 4-vector that Bondi and Sachs wrote down. Well, it's a rather well-known by 1982, after we proved the positivity of ADM mass. We also proved the positivity of Bondi mass. And it was independently done by Horowitz and Malcolm Perry at the same time in Princeton when we were working there. For the Bondi mass, there's an important formula. It's called Bondi energy loss formula. When we differentiate the Bondi mass respect to U, see the Bondi mass is defined by U equal to constant, and we differentiate it, we got the Bondi loss formula, and this is very important. So how does this come out? We expand the metric tensor HAB in terms of the standard metric plus the lower order term CAB divided by R. And then we see we can differentiate CAB respect to U. That's called the New's function. So that's called the Bondi New's function. And what it says is that the Bondi energy is decreasing by the integral of the New's function squared. So this is one of the most important formula that appears in Bondi-Sachs paper. And this is extremely important. Actually, this gives rise to the first theoretical study of gravitational radiation. The linear case was due to Charman earlier, but the nonlinear case is due to Bondi and other people that we just mentioned. Well, so we have a nice, well-defined boundary mass, and that was pretty satisfactory. Once we know there exists a boundary sex coordinate. But the definition of angular momentum turns out to be much more subtle, largely because of several problems that arise, namely the convergence of expansion similar to above, and then the choice of the boundary sex coordinate. We want to prove to make sure that the definition is independent of choice of boundary sex coordinate. So that's two issues we need to address. Well, there are still Killing fields, namely rotational fields, but which are high order near infinity compared to the translation Killing fields, using in the definition of energy and linear momentum. So because it's high order, we need to give a very precise comparison with the Minkowski spacetime in order to find the appropriate definition of angular momentum. This has been a problem for a long time. Many approaches to define angular momentum was proposed. There are Hamiltonian formulation, spinor twistor, Komartai, etc. And here, at least some of the authors that have been working in this, so there are more than 10 people, but there probably you can find more, leading to different definitions of angular momentum. And they, of course, are all important papers because they do give rise to many ideas. And all these definitions have this form, integral YA-NA, where YA is rotational Killing field on S2, where dealing of a sphere. NA is sigma AB, NB, where it is called angular momentum aspect, which is called psi1 in the Newman-Penrose formulation. It appears in a higher order expansion, WA. WA appears in the shifting of the metric tensor on the sphere. So it appears in this formulation, WA equal to this expansion, where C already appears in the previous definition. NA is defined by this equation. So we found out all definition has this form, integral YA-NA, plus ... So these are the important part, the ... part. And the definition that we know, all of them that we mentioned, more than 10 different people, they all recover the Kerr angular momentum in certain coordinate system. So the great Kerr metric gives rise to angular momentum, and it's also, of course, important that we recover that. So all of them recover that. So that's good. But there's a super translation ambiguity since we have no preferred coordinate system when radiation is present. In other words, there's no preferred U coordinate. So the question is, you measure the angular momentum in one boundary sex coordinate, and you use a different boundary coordinate system, you may get a different answer. That's the problem we are dealing with. So to be more precise, you use U bar to be your preferred U coordinate, and then I can translate it by any function fx defined S2. This is called super translation. So super translation appear in this picture by just changing the foliation of I plus. So this ambiguity that appears, we want to make sure that the definition we use should be independent of that. Well, the function f that we just mentioned, the f here, the ambiguity that caused the problem, fx, can be expected. But there's constant term, there's linear term, and then there's a term called s. So linear term kind of corresponding to the standard four-dimensional ordinary translation. And that we know, one knows how to handle reasonably easy. The major problem comes out from S, which is called pure supertranslation. That's what we want to deal with. For a supertranslation, we can calculate, many people have done that. Is m bar u bar x. The mass aspect is transformed in a rather complicated manner, which I write down here in terms of Null function, in terms of the ambiguity f, and CAB is defined here. The good thing is about NAB is rather well defined in the last equation here in 3.1. So this is independent of the supertranslation. Consequently, the total flux of energy, which is come out from boundary laws formula, the energy plus infinity minus energy and minus infinity is equal to the integral of the L2 Null function. This guy is supertranslation invariant because NAB is supertranslation invariant. So the energy radiated away is without ambiguity. So that's pretty good and pretty satisfactory as far as the problem we are facing with is concerned. But on the other hand, under supertranslation, the total flux of classical angular momentum transforms. And this was written down here, J tilde is equal to this quantity, which was discussed by many authors, as I mentioned. This quantity always appears. And it transforms according to this equation. So where the right-hand side is integral of f, ya, covariant differentiator a of m plus and m minus, where m plus minus is mass aspect at infinity. So the flux transform according to that is a problem because the right-hand side actually is rather non-trivial. It could be any number, as long as the F has the supertranslation part, non-trivial supertranslation part, where L bigger equal to 2 spherical harmonic component appears in the function F in the expansion. When you put that in, you can get any number. So this means that total flux of the total classical angular momentum is depending on the choice of the supertranslation, which is not good. So in fact, because of this ambiguity, Penrose wrote a paper in 1982. It's called Some Unsolved Problem in Classical General Relativity. He says that the very concept of angular momentum gets shifted by supertranslation, and it's hard to see in this circumstance how one can rigorously discuss such quantity as the angular momentum carried away by gravitational radiation. So there's a question, a physical question we need to answer. The angular momentum carried away by gravitational radiation. If we cannot understand this shifting by supertranslation, it will be difficult to answer this important question. So there were many efforts to try to eliminate the supertranslation ambiguity by choosing special Null formulation. So in 1986, Maurice chose a nice section, and this is assuming zero boundary flux momentum. And Ricci in 1997 assumed something called preferred cut with zero electric part of the shear. Both of them were only in special cases. Also in their own paper, they wrote down there's conditions that they have to assume. So that means despite they can deal with some interesting cases, it's still not general enough for handling the problem of the question of angular momentum carried away by gravitational radiation.
WeChat audio.
So we need to deal with this, and this was done in 2015, about 6 years ago, that Chen and Wang and myself proposed a concept of quasi-local angular momentum. This was based on the theory of quasi-local mass that Wang and I has been on for many years, since 2009. Actually, this quasi-local formulation is very important for the definition we are putting in on the angular momentum now infinity. Without this quasi-local formulation, we would not be able to come up with the proposal we are making here. Actually, the quasi-local formulation was proposed by Penrose himself in 1982, as he considered these two definitions, the definition of quasi-local mass and quasi-local angular momentum as his number one and number two unsolved problem in classical general relativity. So what are we doing? What we do is that given two-dimensional surface, space-time surface in the space-time, we extract some physical data out of it. One is sigma, which is a metric on the sphere. H is the mean curvature of the surface sitting in the space-time. Alpha H is the connection in the normal bundle of the two-dimensional surface in space-time. So quasi-local means that given this data only on the two-dimensional surface, we want to calculate something called quasi-local mass and quasi-local angular momentum. So what we do is this: given a surface, we want to look at isometric embed it as a reference frame into Minkowski space-time. And we consider the following equation, 4.1, which means that I isometric embed the metric sigma AB into Minkowski space-time. So that's why it satisfies this equation. And then this embedding of sigma into Minkowski space-time give rise to configuration, which I can also find reference data. Namely, sigma is the same as before. H naught is the mean curvature vector. Alpha H naught is the connection sitting in the Minkowski space-time. Based on this embedding, I get two data. One is called rho, as defined here. J is defined in the second equation. This looks complicated, but actually it's very geometric. I don't have time to explain to you why we come up with this quantity in a natural manner. The point is that integration of rho gives rise to the energy of this embedding, which depends on the two sets of data that I just mentioned to you, namely the isometric embedding and also the data come from space-time. Now, isometric embedding is kind of like a gauge, a frame. So in any case, what we do is that we want to get rid of this gauge dependency. We minimizing the energy by allowing all possible isometric embedding X. After I'm minimizing it, I get an equation. Is the divergence equation of J equals 0, 4.2. So what is the setting? Given the local data of a surface in space-time, I isometric embed it into Minkowski space-time as a reference frame. I come up with this quantity rho and J, and can define the energy, and I'm minimizing the energy among all possible isometric embedding. I get an equation, 4.2. This is a very nice and beautiful equation, divergence J equals 0. Now, for surface near the now infinity, turns out the system equation 4.1 and 4.2, namely this equation 4.1 can be solved. The previous one is 4.1 isometric embedding. 4.2 is this equation. These are two equations which we can solve, and we can prove that it has a unique solution. And this equation can be calculated numerically without much effort. So in this way, I get all the quantities including a tau and rho and J. With this, then we can define quasi-local angular momentum. Given a rotational Killing field in Minkowski space-time, we define the quasi-local angular momentum on sigma on our surface as this integral. And then we take the limit of the surface. This one is defined on a finite distance from black hole or whatever it is. And then we take limit of this sigma going to now infinity. And this can be carried out for very general space-time. This is very important because when we define this, we do not need any special structure at now infinity. The peeling structure, which was used by Penrose and many other people, that the curvature decay in certain way, but we actually can define it without those conditions. Now let's compare.
Sorry for the interruption. Sorry for the interruption. You have 5 minutes, please.
Okay, no problem. So the angular momentum classically is defined by J tutor. We are adding a term here. This capital small c is given by looking at the shear tensor CAB. This has never occurred in any previous definition. Angular momentum, it occurs only because when we understand this problem from a quasi-local point of view, and this was obtained in the following way. We decompose CAB in this interesting quantity. It's kind of similar to Hodge decomposition. We find C in this here. So we can solve C and obtain a gravitational ground state. So this additional indefinite J come from reference term in the Hamiltonian theory, actually. And so we prove the following statement in this year or last year, actually. Suppose NAB decays in the right way so that we can define the whole thing. The translation is decomposed into a linear part plus S part. Then we look at the total flux of the angular momentum. It turns out it transforms according to this quantity. And this transformation is exactly what we expect when we are dealing with angular momentum. When you see things around by a movement of the center of gravity and all that, it translates according to this. So therefore, in particular, we have found a quantity where del J, the total flux invariant under pure translation and the transformation law, is same as a special relativity's angular momentum. This condition of decay of NAB is needed even for the convergence of del J Y. So it's needed. So this here we have complete our task in the following way. We obtain a complete set of 10 conserved quantity, energy, linear momentum, and angular momentum, and also center of gravity. And this has a nice property that we can calculate numerically now infinity, and it's not hard to calculate at all. And this quantity all vanishes for any bounded Sachs coordinate system of the Minkowski spacetime, since it has to vanish because there's no gravity on Minkowski spacetime. And also, we recover the mass and the angular momentum in the bounded Sachs coordinate. On a general spacetime, the total flux of these quantities are super translation invariant. That's a task that I was set out to do, and this turns out to work out. And the flux transform according to basic physical law under ordinary translations. So we are pretty pleased of that. And this, since it's the only angular momentum definition that I know of, that's independent choice of bounded Sachs coordinate. And I think, first of all, they can be computed in any bounded Sachs coordinate as a result. And I believe this should have an interesting physical meaning. And this would be interesting to calculate for more general quantity, for data to come from experiment, which we haven't done yet. But I think that would be very, very interesting questions and interesting properties that we like to see in the future. So I will start here.
Great. Thank you, Professor Yao, for the informative talk. So we have time for 1 or 2 questions.
Yeah, can I ask a short question?
Sure, go ahead, please.
Yeah, my name is Maurice. Thanks for your very concise exposition. I was wondering if either a priori or a posteriori, you can say something about the connection or correlation from an observational point of view between the definition of energy and angular momentum, insofar as there are subtleties in the definition that you explained?
Well, I mean, there's some important questions we like to prove theoretically. There was a question whether the angular momentum, the size of it can be dominated by the mass. This is a rather famous question that we like to prove. We haven't done it yet. But of course, special case is known to be true. There's very subtle addition term, like the C that we mentioned here, is rather intricate, and we like to explore much more. We like to calculate much more about them. So
May I have my own question?
What?
Hello, may I have a question?
Yes.
Well, the answer is ongoing, I think, no?
Yeah, I guess we can wait till the first question is answered. Sorry. Yeah, go ahead, Professor Yao, please.
Well, I mean, the first question is that we think it's a great question, but we are working on it to get more properties about this new definition of angular momentum. We certainly have a lot of properties about the quasar local mass, which we have been using. But the relation between quasar local mass and quasar local angular momentum is still being explored.
Great. So, Professor Subuti, you can ask your question.
The angular momentum, when it is defined, it obeys certain symmetry group. The way Professor Yao is changing the definitions, how these symmetries change, or they stay the same, or what happens to what is the symmetry of the definition that Professor Yao is given to angular momentum, which he defines?
Well, I mean, the symmetry comes from supertranslation, which was defined here. There seems to be some misunderstanding by people in the physics community. It's very simple. F is defined, the ambiguity comes from F. This is supertranslation that appears in a problem that calls all people to work on. So this F is decomposed. Is it U equal U bar plus Fx? Whatever symmetry group you call it, it is related to how U changes, and F is the supertranslation. And then what we did is we decompose F in the linear part plus S. So the linear part you can say is Lorentzian transformation or whatever. And this is a smaller group, but the big group is with S here, the pure translation. And so we are handling the symmetry according to this supertranslation. I don't see there's any ambiguity or any misunderstanding supposed to appear. So we found a quantity that is invariant under this supertranslation.
Great, thanks. So for the interest of the time, I guess we can stop here. So let's thank Professor Yao again for the nice talk. So we go for the third speaker of this session. I don't know if the speaker is ready.
Yes, I'm here.
Oh. Okay, so the third speaker is, so can you please share your screen also?
Let me see. Okay.
Okay, so it seems to be okay. Yeah, so the third speaker is Professor Jorge Rueda, and he will talk about gravitomagnetic interaction of a Kerr black hole with the magnetic fields as the source of the high energy radiation of gamma ray burst. So Professor Rueda, go ahead, please.
So good morning. First of all, can you see my screen and hear me well?
Yeah, I see your screen and hear you well.
Okay, thank you. So, okay, first, thank you very much for inviting me and allow me to present this recent work, which actually based, most of it based in work in preparation to be submitted in collaboration with Professor Jorge and Kerr, and I'll take also some information from a previous work that I published also with very morally. And so everything is about the interaction, the gravitomagnetic interaction of the Kerr pole, which is immersed in a magnetic field, and how it can develop and develop a mechanism which becomes a source of the high energy radiation in GRBs. So we try to answer these three questions. So can we use an electromagnetic process to extract the energy from a rotating black hole? So this is the big question we are going to answer, and the answer is yes. And to do that, we have to introduce what we call the inner engine machine, and inner engine of gamma ray bursts, but not only, because it also applies to the case of particle active nuclei. So this brings me to the second question: what kind of emission as we will see, is mainly a synchrotron radiation, and mainly in high energy photons. So by high energy, I mean here of the order of GeV energy. And can we give specific examples? So first I will introduce more theoretical framework, so a qualitative picture of this mechanism, and then we move at the end to some quantitative examples. So let me start with this summarizing slide. Say, I think first of all, we showed it yesterday in this talk, and so I will describe it. Start everything from this what we call a binary-driven hypernova. So this binary-driven hypernova are the end stage of evolution of a binary, of some compact binaries, which is shown here. You can see along this left side of this image, this binary evolution is starting through the massive stars, which they go, as you know, through different stages in the evolution, which they become first an X-ray binary, then they can go through multiple common envelope phases. In these phases, they become more compact, the orbit. Then the main after the X-ray binary phase, then this almost ordinary star from a carbon-oxygen core and compact orbit. Then we aim at the second stage of the second supernova explosion stage, and this is where the action starts, where we locate the GRB progenitor. So we have the XEO core, the carbon-oxygen star exploding a supernova in presence of a neutron star containing very little matter. So here, in this explosion, Laura Becerra presented some of the numerical simulations that we have performed of this process, in which the supernova explodes and produces a very massive accretion onto the neutron star companion, how the neutron star companion evolves and creates both energy and momentum, and eventually becomes a black hole because reach this critical mass. So then, as you can imagine, you see all these possible observables that come from this process. But in this talk, will be interested only on one part, in which once the neutron star becomes a black hole, so it is immersed in, you can imagine and see actually here is the neutron star that is becoming a black hole. It has created a sort of low density environment around, and is immersed in the magnetic field. So what happens in this situation when you have a black hole immersed in a magnetic field, a three-dimensional magnetic field, and you have particles around actually a very low density ionized plasma? This combination of the three ingredients is what we call the inner engine. And in this inner engine, what we be responsible for the high energy emission. So there's here a list of theoretical work that we have been presented in the last 10 years, from 2012 to through this year. Actually. So this is not a full list of works, but it is only confine myself to the theoretical work we have developed, and which have allowed us to reach this point. So how did this? What is the high energy radiation of a GRB? So let me show you this example. This is a beautiful example of the GRB 1901 what you see here is are the light flows. So you can see here both not only the gamma ray paths. They not only emit in the gamma ray, but in the gamma MV radiation, but also GV radiation, but also optical emission, optical X-rays, and the radio. So but this talk can confine again only to the high energy component, because for the X-rays, the radio, optical emission, we have there's another mechanism that works again within this system of the binary hypernova, but it's not related to the emission of the black hole or the emission of this inner end. And the emission in the MEV radiation, which is related to the from emission of the GRB, again is somehow connected with this with part of this of my talk, but it's not the topic of my talk. And I don't know, probably Rahim Morari will speak about it in this meeting. So I would like to highlight here from this video, we see this the high energy radiation is it comes as a power law. Is this line here over here is this power law with an index slope of roughly minus 1.2. More clearly, you can see here in this plot. This is the GP radiation of 1.14, but it's not only intervening in 1.14. Actually, you can go and see if all and study all non-GRBs, energetic GRBs with energies above 10 to the 22 energy release, what we call the binary fusion hypernova type 1, and study and see that actually all of these kind of power behavior in the 0.1 GeV energy band. So this is just because this image I taken from recent work in which we compile all the information that is known on the GeV radiation from the objects. But it's important to highlight here is that from this study it turns out that not all non-GRB is energetic GRB. We had some observed effective GeV radiation, but from these and from these statistics, we can infer that actually this GeV radiation should be emitted in a cone with half opening angle, about 60 degrees from the normal to the orbital finally. This is a very important information, as you see in a moment. Actually, the theoretical model implies that it should be this region in which this radiation should be produced. Actually, from the theoretical point of view, we don't get 60 degrees, but something like 55 degrees or something like that, very closely. So we're speaking about this. This is LTV will work. Yes, this is a video on the simulation of a formation of a binary hypernova. So you see this floating. This is a floating supernova, and how this is the neutron star going around and getting the radiation, and then this cleaning up this region, creating a low density region around it. And while we are simulating this, we are accounting on the accretion process in the neutrino emission that allowed us speaking about yesterday, and how this emission neutrinos allows the neutron star to continue to accrete and to eventually reach the star critical mass of a black hole. Then let's go to what would be this new system in which you have the black hole immersed in a magnetic field and with density around. What we first is we will make use of the world solution in 1974 that will be enough with a solution in which you have the Kerr solution for background, the black hole solution, and you have a test in principle, because we don't need to modify the geometry by the of the magnetic energy in view of the, because the magnetic fields we have in mind is not are not enough to do that. So it's enough to take a test electromagnetic field, and here is the solution by the zero angular momentum surface. So you have the components of the electric field and the components of the magnetic field. So actually, you have all the rotation, so you have on the spin a magnetic field, but these systems induce electric field that you see here. This electric field is much as a Faraday disc, in which you induce this magnetic field that you will see in a moment is of quite polar nature. This is a picture of the electric and magnetic field lines around the black hole. This excellent that this is a Kerr shape coordinate that Professor Kerr showed this morning. We make this transformation to represent the solution of this coordinate, which is appropriate for a picture representation. So what you see here, so these orange lines are magnetic field lines, and these gray lines are electric field lines. So you will see clearly this is a magnetic field. You have this magnetic field aligned with the whole spin. You have here the magnetic field is pointing up. So they are aligned and parallel. And in that case, you have a region in which the electric field is pointing inward. And then there is a change, a reverse sign. You see here inward, and then you have a region which is outward. You have again inward, outward. Okay? And you see the colors of the background representing the intensity, how intense the electric energy. So this is important, this inward, outward behavior. This inward electric field means negative particles will move outward here, moving inward here, and so on. And the use situation, of course, is equatorial symmetry. Of course, as we expected, the use of the Kerr solution. So this is the region in which we expect particles to move outward, and so to emit a radiation through that goes to infinity. In fact, if we are going to compute the solution from this, a solution where the change of sign occurs is in fact very close to 60 degrees. So, but this is not enough to say that all this solves the problem. 50 degrees stating is exactly what this is the initial. So the problem not is not enough. Now we have to study the motion of charged particles and the radiation of charged particles in this region to see actually if we can, if it comes out exactly what we see. So this is the inner engine. So again, the Kerr hole, there's a totally uniform magnetic field and very low density plasma with densities starting from 10 to minus 6 centimeter all the way to 10 to minus 14. So extremely low density. This is a plot that shows the quadrupolar measure of the field. The field is a sort of there's a surface charge. The system is not charged actually, but this is some people find useful this kind of understanding. You see these sort of patches in which you say inward, outward, electric field, inward, outward. So we can make a representation of this as a different surface charges on the black hole horizon. You can do that by introducing this surface charge density, which is actually the radial component of the electric field, and you can see actually that it has negative part, positive charge, and negative charge as a function of the polar angle. Actually, you can also even integrate this surface charge and compute that what would be the charge in each of these patches. And actually, in fact, we can show that the net charge is 0. Some of these two is to this charge. We will not make use of this. This is not needed, but this is just to show you this, that it actually allows us to understand this particular electric field. The electric field energetics, this is what matters here, because the electric field will accelerate particles. With the electric field, the energy which is stored in the electric field, which will allow us to accelerate the particles. So this is an estimate. It turns out very accurate. Actually, the energy which is available for acceleration, given by this extremely simple undivided quantity. So it depends on the magnetic field, the zero, the angular momentum of the black hole, and the mass of the black hole. The maximum particle energy available is given by this simple expression. This is the difference of potential electric potential energy from the horizon to infinity. But this is the energy that the particles can attain from the horizon to infinity, and eventually by acceleration they will radiate and emit this radiation. Of course, someone has to pay the price of this energy, and who pays the energy is the black hole, of course, because this electric energy is associated, is coupled to the mass and the angular momentum of the black hole. So this energy which is radiated, angular momentum, which has to come at the expense of the black hole energy and angular momentum. So we will see that in a moment. But I would like to right away that black hole energy, so the energy which can be emitted has to come from what is called extractable energy, extractable black hole energy, which is the difference of the mass energy of the black hole with the reducible mass energy of the black hole. You cannot calculate this without introducing, of course, the black hole mass energy formula, which is given by this for a Kerr black hole. So let me move forward. So we'd like to introduce here the equation motion of the charged particles in this system. So these are general. This is the equation motion for test particles, charged test particles, including the radiation reaction, of course. And this is a specific with the zero angular momentum observers. And the important point here, the radiation reaction is actually even if it looks somehow complicated here, it's in lambda form. Actually, the dominant term is a symbol like this, which forms after they show you exactly the form, very similar to what is in flat geometry. You can write this formula in this regime, which is quite accurate. It's a quite accurate approximation for this equation. You have in mind, so this is the evolution of the Lorentz factor and the evolution of the particle partial components. And you see here, the first are the, let's say, the flat terms that looks exactly like the flat terms, and then it comes out of this GR terms. This is the same. Now, for the photon for momentum, at infinity, as in infinity, we would like to see, actually, we would like to compute the radiation at infinity. So these are the photons. This is the photon for momentum. So they have photon energy and three-dimensional momentum component. We will see here. What actually is important to highlight here is how the formulas that we look also again as awful and cumbersome and complicated. Actually, when you look carefully, they show us exactly what we know from the Minkowski space-time action. The radiation is confined for a particle which is accelerated toward the observer. The radiation is confined within a cone with an angle which is roughly 1 over Lorentz factor. So this is and equations just show that, with the exception that there is an purely relativistic effect here, which is due to the frame gravity. it is the azimuth component, but actually, even if you cannot cancel it, the only way to cancel it is to put zero rotation. But this actually is not dominant. Is negligible with respect to the other terms. So we can apply what we know, assume that the radiation is actually confined within 1/τ. This is an example. This is how this is a numerical integration of the motion for particles. Actually, you see this is exactly what you expect. So you see the particle going around the magnetic field line, going making a spiral, but at the same time it is rotating and so it is accelerated by the electric field, but then it is very rapidly start to follow actually the magnetic field line and going making a spiral, so we can see the contribution. This doesn't happen. This doesn't happen along the black hole rotation axis because the electric field and magnetic field are they're parallel. So actually along the polar axis, we don't have essentially we don't have radiation. The particles can just accelerate, and this is extremely high energies. Along this is what here, and they can be actually sources of ultra high energy cosmic rays. While at different angles, the electric field and magnetic fields are not parallel, and they produce this spiraling of the particles along the magnetic field lines and incredible radiation.
Sorry for the interruption. Sorry, we have 5 minutes left, please.
Okay, thank you. So of course, this radiation, the electromagnetic energy is radiated, and of course it is coupled with the black hole angular momentum. So actually, it is also extracted angular momentum at the same time. So this is the evolution of the slotted factor. This is actually proper time. This is you can see what is important to see here. This is actually extremely low time, as seen by infinity. I will show in a moment. This is an asymptotic slotted factor, constant value, because you have the competing effect of acceleration and radiation. At some point, they balance is shorter, and actually you get this asymptotic value. This is the characteristic photon energy of the radiation. As you can see here, is actually it goes to the gain to somehow between the Jeff and tensor between the GeV and tensor. This is the photon component. This is what I told you before. So this is essentially 1/gamma, and the azimuth component can be neglected, and so we can compute the power as usual. This is the volumetric power of this radiation. So this is for a single particle. These different colors are particles starting from different angles to the polar axis. So actually, this is where 1 degree. This is 1 degree, 14 degrees, and 27 degrees. And again, this is here. This is because that's a particular Lorentz factor is an asymptotic power, which will be of interest for us. So we saw there on 10 to the 12 and 10 to the 13 per second. But this is the spectrum. So the spectrum, as you see here, the spectrum is peaking at energies of the order of the GeV. And I will try here to estimate what will be the DMC of the system, assuming that you see here, this is the density of electron that can be actually accelerated by this system, because you see this is the electric energy density divided by the energy. Of course, your systems can have more particles than this, less particles than this. But this is the amount of particles that the system can accelerate. And by looking into this, you see actually this of the order 21 per second per cubic centimeter. And this acceleration comes already near the black hole horizon. So actually, for a stellar mass black hole, if you take into the order the volume near the horizon would be on the order 10 to the 19 centimeters, so actually multiplied by that, and what you get is exactly 10 to the 50, 10 to the 51 error per second of luminosity. This is exactly what we need. So this system has the power to emit a luminosity of the 10 to the 50, 10 to the 51 error per second at GeV energy. You can see here the radiation time scale. This is exactly what I was commenting. And this is your half acceleration, and then competing with radiation time scale at the end, reaching an equilibrium. And this is the radiation time scale becomes of the order of 10 to minus 50 seconds, extremely small, which is the time scale of the synchrotron radiation actually. In fact, if you take a Lorentz factor of 10 to the 4, the energy is 10 to the minus 1 erg for this electron. And the radiation power is 10 to the 13 erg per second. It implies a time scale of 10 to minus 14, which is exactly what is shown here as typical. So some numbers for the polar emission. So there is no synchrotron radiation, just acceleration. So the electrostatic potential of the order of 10 to the 18 electron volt for a stellar mass black hole. Then the power is 10 to the 42 erg per second. This is academic. A short comment, actually, if you compute the number of particles that can be accelerated per unit energy per unit time, this system gives you a really beautiful formula which depends only of the fundamental charge squared, inverse proportional to the fundamental charge squared. But we here as a standard candle, okay, this is the quotation mark, the sense that this is universal. Then the polar emission, I mentioned already, this is synchrotron radiation of GeV energies. This is the color plot showing pitch angle. So the angle between the initial velocity vector of the magnetic field is related to the characteristic energy of the photon. So this is for the pitch angle that we have in our system. We have exactly all the radiation components. And this is the picture at the end. What we have for this, I showed already. Actually, this is the region where all these pitch angles, where you have this pitch angle and GeV energies, and this is everything comes in between these 55 degrees. This is the table showing the numbers actually for 1901 for as an example, or the scale in the case of GN, so for 1901 solar massive black hole, but different, of course, different scale of magnetic field for a GRB, for IGN, the order of 10 to 100, 10 to the 3 Gauss, depends from case to case. But everything, the system, of course, you can imagine if you require unit is a magnetic field in a trading black hole and some particles around. This is the only thing you need for this system to work. So this is a summarizing slide.
Sorry, the time is pretty much up, so yes, we are
okay. So this is, so let me finish with this. Maybe we can finish with this slide. This is a mechanism for black hole energy extraction, in which you emit this energy actually by extracting bit by bit energy from the black hole and the angular momentum from the black hole from this radiation at the end. When you integrate this, actually, this is the fraction of value, some fraction of mass and some fraction of momentum, of angular momentum time by time, as these particles go over and over. So these conclusions, there are essentially, I mentioned everything already, and so I'll be happy to take your question now. Thank you.
Okay, great. Thank you very much for the informative talk. So we have time for maybe one question. I guess we are somewhat behind the schedule, but we can have one question.
Hello, can I ask a question?
Sure, go ahead, please.
Thank you for the nice talk. Actually, the observations on much larger scales indicate that the magnetic field configuration can also be affected by the black hole's gravity. I mean, it should be parallel to the accretion material, accreted material. Have you also tried this configuration?
I'm not. When I Let me try to clarify one point. When we look at the motion of particles, of course, we are taking into account both gravity and the Lorentz force at the same time in the R. What I mean by ISS field is that I don't modify the geometry of the geometry. I mean, the Kerr background, but not the magnetic energy should modify the background geometry. It's different. It's a different thing. To do that, I mean, we are speaking here about a magnetic field of 10 to the 10 Gauss. Actually, to modify the magnetic the geometry of a stellar mass black hole, it should be something like 10 to the 21 Gauss or something like that.
Okay, thanks.
Okay, great. So I guess since we are behind the schedule, we can stop here. So thank the speaker again. So I guess this session is over. So we had 3 nice talks here. And I remember the first talk, there was a lot of discussions. And unfortunately, we didn't have much time to continue the debate between Professor Kerr and Professor Subuti and Professor Ruffini. So I guess, so I leave it for Soroush. So if you want to decide the discussion continue, please go ahead.
Thank you, Hassan, and thank you all the speaker. Yes, I think we can have, if we have Professor Subuti. Professor Subuti, can you hear me?
I do, yes.
Could you please repeat your question at the first talk?
Look,
Then,
first, let me say that I wasn't debating with Professor Kerr, except
yes,
that one of the audience, one of the audience raised the question of inviting in Lewis' equation. Lewis' equation deals with distributions, sort of a probability density in phase space. And it has extension. It is a distribution. It is not a one-point particle entity. And all singularities, in my opinion, in physics, wherever they are, they stem from the fact that there is a tacit assumption of point particle in classical mechanics, in electromagnetism, in Schwarzschild metric, in many, many places. This singular point particle is the source of all divergences. If you could abandon this idea, then you will not have divergences anywhere, including in quantum electrodynamics. And life becomes much simpler to deal with. And the way to get rid of this point particle assumption, I'm doing my search on my own problems. For instance, when you're writing Schrödinger equation, you're assuming that there is a particle with a wave function, which is a distribution. On the other hand, in the Schrödinger equation, you're inviting in the Coulomb potential, which is a singular point. You're allowing Coulomb potential, a singular point, to act on the wave function, but you are not seeing any reaction from wave function on the electromagnetic field. You could get rid of it by assuming that a particle with quantum wave function and electromagnetic properties have a mutual interactions between the two fields. the same way that you are entering electromagnetic field into Schrödinger equation, you could introduce Schrödinger equation into electromagnetic field by simply requiring that there is a mutual interaction between the two waves. And this removes the singularity that QED deal with by throwing away divergent integrals by invoking scalars, scaling symmetry, and so on and so forth. This is my own work on I'm doing for myself, but there was a mention of by one of the audience of Liouville's equation. Liouville's equation is a distribution. If you could make a mutual interaction between Liouville's equation and wherever you're seeing the singularity, singularity will be removed. That's my point.
Sorry, can I interject? I brought up Liouville, but I brought up Liouville's theorem. I'm not sure. I think we're talking different things, I think.
Can we start the... we are perfectly on time. And
Professor Ruffini, can you hear me?
Yes.
Just can we hear Professor Ruffini, Professor Kerr comments about this, because he wanted to add a comment on this.
Okay, but then we have to start because Klaus Lammerzahl is just arrived. Of course, at any moment, Roy, as president.
Please, Professor Kerr, can we have also your comment about what Professor Subhuti mentioned?
It's really hard for me to hear. Okay, my hearing is not good, and it's the what's coming through is difficult. Am I being told that that there are singularities because of distributions and quantum mechanics and all that jazz, or what? If the speaker disagreeing that there's no proof that singularities exist in neutron stars, for instance, is he agreeing with that, or is he saying that for some reason there's got to be a singularity somewhere?
No.
But if we're going to go right down to the lowest level, then quite obviously either you have point sources which are have which are of zero volume and therefore everything's singular there, or you have quantum mechanics or something else. I don't know, but I'm not talking about singularities at that level. What I'm saying is that if you don't believe that an ordinary neutron star has got some singularity inside, why do you think that a black hole, which is just a neutron star with a rather stronger gravitational field around it, why do you think that's got a singularity? So I certainly, if we're saying that everything in the universe has got a singularity, whether it's even my poor little pussycat's got a singularity, I presume, of some form. So if I could hear better, I might know what we were talking about. That's the real problem. What do you say, Raymond?
No, it's okay. Part of this has been addressed by Jorge, and I think the key point is also the asymptotic solution outside, which is the presence of the magnetic field. And I fully agree with you that we have to precisely to look at the formation of the black hole, which comes from accretion into an already existing neutron star with a very strong magnetic field of 10 to the 12 and up to 10 to the 14 Gauss asymptotically. I think this has been clearly pointed out and which we evolved in our joint paper. I think if we may, thank you again for the intervention and the beautiful talk by every presentation. I'm very impressed also by the one of Professor Yao, which has been very exciting.